Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Alright, step on inside here. We are going to look at geometric series. We've done arithmetic sequences, geometric sequences, and arithmetic series. Now it's time for geometric series, both finite and infinite. That's right, unlike an arithmetic series, you can have an infinite geometric sequence that can converge at some value. Now, this is going to assume that you've kind of seen or you know something about all the other segments leading up to this, that you understand what sequences are, you understand what series are, you understand a little bit, I mean, maybe not geometric series, but you understand the idea behind series. I'll provide you formulas for geometric series here, but you really know a lot about the geometric sequence, the idea, the explicit form, things like that. And then we can really dive into it. So I'm going to, let me get this set up one quick sec here. This is all good. All right, taken care of. Okay, so in terms of getting this thing up and running, we are going to have two different pages of this, 6 problems on this front where we have finite geometric series. These series end at some point. They terminate when it comes to number of terms. On the backside is infinite, which will go relatively fast once we break down all that there is to be had. Okay, so let's start things off here. Evaluate each geometric series described. Now, the first two problems here, what you're going to have are the value of the first term, the common ratio, and the number of terms. Boom, boom. The next problems here, you're going to be provided sigma notation. Now again, or summation notation. This is assuming you've seen this before. All right, but we've done something with this. I'll explain it again briefly. I'll give you an idea and heads up on what you can do, but we're going to be using these as well. By the way, you might want to have a calculator on hand for these ones here, especially if we don't go for a precise answer when it comes to a fraction, just because the fraction might be harder to reduce, but we'll look at that. And then we'll look at ones where they're actually lists, and then we got to figure out how we're going to eventually break that down when it comes to its notation and what we want to do with that. All right, so those 6 problems, but those 3 pairs of problems. So in order to do all these, what we need to know is a formula for evaluating. I mean, listen, if we were provided, because I want you to know what this thing means, the value of the first term is -4. The common ratio is 4. That means that we'd have to multiply this thing by 4 to get the value of the next term, which would be -16. Multiply that by 4 and you get -64, and then -256, and this goes on and on. Let's see, do I know the other ones? -1024, -4096, and I don't know this last one. But notice what I'm doing here. I'm not putting a comma in between these because this will be a series. Hold on, 4096 times 4. 16384. So these 7 terms are going to be added together, or subtracted if you will. Just they're all negatives, and adding a negative becomes subtraction. And basically I want to find out this result here. Now yes, you can use a calculator and type these things out, but at some point I could ever ask you what about the 70th term. I could ask you a bunch of different things that makes this harder to do than not, and you'd have to know that this is what's happening. I hope you do. But furthermore, the reason why I'm doing this is so you know what kind of answer to expect. A negative one and a large one. That being said, this is what's happening. We're finding this results of all these sumwise, and there is a formula that we can use to evaluate this without actually having to type these in, and problem dependent, without having to actually discover all those numbers in and of itself. And it's this: to find the value of your finite geometric series of n terms, we are going to take the value of the first term, multiply it by the difference of 1 and your common ratio raised to the nth power, n being number of terms, divided by 1 minus the common ratio. I'm not going to spend time on the proof for this thing. My students have seen it. They probably were a little too freaked out by it, and I don't know if they learned more as a result, but just to show its existence, there it is. So this is our formula we're going to be using, which means we need the value of the first term, we need the common ratio, and we need the number of terms. Check, check, check. So we can substitute these in, and this will find what it is that we need. So on number 1, we can find the series for this geometric sequence with 7 terms if we take the value of the first term, -4, multiply it by 1 minus 4 to the 7th power, divided by 1 minus 4. Now, I've seen varied answers from my students, and normally it's an order of operations thing, especially when going to the calculator. That's why I generally recommend that you simplify things slowly as you go. Yes, you could type this all in the calculator and get it done in one fell swoop, and although I only have a calculator right here to kind of work with you on this, let me see if I have the ability to see this when I zoom in with you. Will you be able to see things if I type it? Let's see. Yeah, we should be able to. I have my other one, but on the computer it's a little sluggish and slow. So when I type this stuff out here, if you type this exactly, you're probably going to have some issues because you're not taking care of the denominator properly. If I type this out right here, I have a problem. I'm only dividing by 1, and then I'm taking my answer and I'm subtracting 4 from my answer. This is going to give me an answer of this right here. Now here's a reason why we should know that this answer is wrong. The answer is positive. Positive 65,000, etc. We should be getting a negative answer here. As you remember, negative minus 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 minus. This should be a further negative answer. So the problem is we're not taking 1 minus 4 and subtracting all told like that. So it's better to clean some things up. If I were to do this on my own as far as cleaning up, I would at least get that 1 minus 4 into a negative 3. Pretty straightforward math to do there. 4 to the 7th, I don't know. Oh, 16384. It's that number. So 1 minus 16384 is negative 16383. So, maybe you can type this out in the calculator, and you even know that 3 negatives leads into a negative. That's even further helpful. Because nothing else here really reduces very well. I mean, it all divides by 3 in the end. So let's see, 1 minus that answer there, and then times negative 4, and then divided by negative 3 right here. So negative 21,844. And if you try it in this form right here, you'll get the same thing, and some people might argue this would have been faster. Remember, you would have needed these terms, but so you'd have to get them yourself, and you'd have to know how to get them. But arguably, this is faster with only 7 terms involved. All right, let's go to number 2 here. Same formula applies right here. Now this idea with a common ratio of 1/2 means we're doing 8 and then plus half of 8 plus half of 4 plus 4 to the 4th term, 5th term, 6th term, 7th term, 8th term, and 9th term. And in the right hands, I would probably request this kind of answer to be a fraction. But given that we can get an exact decimal because all these numbers here don't repeat their decimals here, we'll probably just put in the decimal answer. But this is what we're trying to establish right there as we type it all out. Now, formula-wise, it would be S sub 9, that's 9 terms, right? And that was 7 terms here. S sub 9 equals the value of the first term times 1 minus. Now, here's where typing something in a calculator can get a little tricky. 1/2 should be in parentheses there to the 9th power divided by 1 minus 1/2 here. If there were things I could clean up before typing this stuff in the calculator, I would probably figure out what 1/2 to the 9th power is. And by the way, 1 minus 1/2 is 1/2. And what happens when you divide by 1/2? You multiply by 2. So let's take divided by 1/2 and let's just multiply that 8 by 2. We turn this into times 2, and that gives us 16. So if there's something to just kind of, again, help you when it comes to order of operations biz, that can be one of them. Now, 1/2 to the 9th power is 1 to the 9th over 2 to the 9th, and 2 to the 9th I believe is 512. So it's 1 minus 1 over 512. At the very least, I could just write this, even if I don't want to figure out that that's 511 over 512, etc. I think that this should be able to pan out the way that it does. And we can double check our answer just by seeing what kind of number we're looking at expecting. I'm expecting a number close to 12 plus 2 is 14, plus 1 is 13, plus etc. And I happen to know, telling my students here, that this number shouldn't go more than 14 overall. This number shouldn't go more than 14. So we'll see how that thing pans out. Because you're taking half of a half and adding it over and over, and it just approaches 1. So what is 16 times 1 minus 1 over 512? Oh, sorry, it shouldn't go over 15. Hold on, did I add something wrong? Oh, 14. Oh, plus 1 is 15. I'm sorry. It shouldn't go over 15. Over 16, I should say. My bad. So this is exactly 15.96875 right there as an exact decimal. You shouldn't round something if it's exact from that, okay? So that would be the exact answer there. Sorry for stumbling upon that. Plus 1 is 15 already. All right, number 3, same-ish, only represented differently. We have, from the 1st to 9th term, this sequence being applied. Now, if you're going to use the formula the way that we did, or at least the one where you're not spelling out every single term, which I could ask you to do, plug in 1 for n and 2 for n. Basically, what's happening is you well, here, we have to find the value of the first term anyway, right? In this formula, we need the value of the first term, common ratio, and number of terms. So the value of the first term, a sub 1, is negative 5 to the 1 minus 1 power, or 0 power, which is 1. R is that negative 5. If you've noticed how this is why I said you have to know a little something about geometric sequences. The way the geometric sequences work is the common ratio is the value that you would be raising, that would be the base that is raised to your variable power, right? That's the common ratio way of there. And n is the number of car alarm going on. And n is the number of terms that exist in your sequence. From 1 to 9, that is 9 terms. So we had to spell these 3 things out. So we have the 3 bits of information we need for the formula. The idea of this would have been starting from 1 and then multiplying by negative 5 to get negative 5, multiplying by that to get positive 25, and then minus 125. And it would keep going this way for 9 terms. Now I will avoid writing that this time, and let's go straight into the formula. So s sub 9 is going to be the value of the first term, 1. That'll be pretty straightforward, times 1 minus negative 5 to the 9th power over 1 minus negative 5. Now remember, on top, 1 times anything just makes that go away. So I'm good without really using that, right? So just ignore the 1 there. That's fine. Now, on the bottom, subtracting a negative becomes addition. So 1 minus negative 5 becomes 1 plus 5. That becomes 6. Should I do the same thing up top here? Should I turn this into 1 plus 5 to the 9th? And the answer is no. That's not to say that this won't happen here. It could potentially, because it depends on what degree you raise this power to. But you can't subtract the negative first. You have to subtract the result of what this thing becomes. And it's possible that a negative power raised to an exponent can turn positive if you raise it to an even power. That being said, this one's not an even power, but it's unwise for you to assume that it's just going to turn to this. It's better that you actually evaluate what's going to happen up here before you move forward. And I don't know what 5 to the 9th is. It is a big number. So this will be negative 1953125. You're going to have to be understanding of the fact that we are going to get a lot of answers in series or sequence when we want to look a little farther out than just 4 terms or so, that the numbers are either going to be incredibly large or incredibly, like, fraction small. So just be used to the idea this is going to happen. So 1 minus negative that is 1 plus that, right? So that's 1953126 over 6, and plus 1, hold on, plus 1 divided by 6. That gives me 325,521. 325,521. And, you know, one other thing about problems like this is, let's say you get an answer that's a decimal or fraction. You know, building the list that I started to build here, 1 minus 5 plus 25 minus 125 plus, you know, this one. Oh, what is next? It's 3 1 something. Again, or 3, I don't know. 31125. Anyway, I think 31625. 3062. Who cares? The point that I'm making with this is my answer should be an integer answer. These are just integers that are adding and subtracting. If you get a decimal here, you miscalculated something. You used a formula incorrectly. I don't know what it was, but something wrong happened. Why should I get a decimal out of adding and subtracting integers? I mean, I shouldn't, especially as the numbers keep growing. There's nothing that's going to turn it into a decimal or fraction at any time in this particular problem. Other problems? Sure, maybe. Not this one. Not number 1. Number 2? Yeah, I understand why there's a decimal there. That's why spelling it out can help making sense of what your problem is giving you. All right, number 4, from 1 to 7 of, we're using M and not N. Does that matter? No, not really. You'll still go up by 1 each time if we do this. Now this problem here does start, if you know, we have to find a sub 1 anyway, but if you know this is our geometric sequence with a sub 1 times r to the n minus 1 power, that this actually is your a sub 1. This is the value of your first term. If you don't, plug 1 into here, right here, and 1 minus 1 is 0, and negative 54 times 1/3 to the 0 power is negative 54 times 1, which is negative 54. Now in the last problem, we also had this same geometric sequence formula. It was the n minus 1 power, but you couldn't see the a sub 1 term. You'd have to kind of know that that's a positive 1 that's right there, which leads us to that one. And then this is the a sub 1 that we see right there. What point was I going to start to make? Oh, so every other term after this from negative 54, we take a third of that, and that's, 18, and then 6 and then 2, and then 2/3, and then 2/9, and then 2/27, all being subtracted, by the way. This is the calculation that's going on, and as you can see here, we are going to be left with some fraction bits, some decimals. And this one, though, 2/3, 2/9, 2/27, those are repeated decimals, so an answer that we get here in decimal form will not be exact. It'll only be approximated. For my students' sake, they kind of fits with me asking them to try and reduce an excruciatingly large fraction over fraction bit here. I'm going to play with it a little bit, but I'll be okay with rounding to 2 decimal places as well and seeing what that answer is. Likely, if they're tested on a situation, I won't give something like that, or I'll give them a decimal common ratio. So just say, hey, just work with that. We'll get an exact answer. So that's fine as well. But the value of the 7th term here, we're going to take the a sub 1 and multiply it by 1 minus the common ratio raised to the, 7th power? Divided by 1 minus that common ratio. All right, 1 minus 1/3 is 2/3. Right there. Dividing by 2/3 is the same as multiplying by 3/2. So what I'm going to do here, a couple things. I got to take negative 54, and I'm multiplying this thing by 3/2, right? Dividing by 2/3, multiplying by 3/2. And then inside here, we got to do 1 minus whatever 1/3 to the 7th power is. Now, 3 to the 7th power, is 2187. So 1 minus 1 over 2187. So if I were to just, I'm going to still work on breaking this thing down, simplifying it. At some point, you can use calculator, your call. If you trust your ability to use parentheses where you're supposed to, you'll probably already have your 2 decimal places answer. But I'm going to keep working on this one right here because I'm going to work on reducing the fraction regardless. Negative 54 over 2 is negative 27. And negative 27 times 3 is negative 81. So on the outside here, I have negative 81. And then inside here, apparently I have 2186 over 2187. So, this is what we're working on now, right? That over that. Now, as a decimal approximation, that's going to be, I'm assuming I did all the math right leading up to that because I haven't done this sheet yet. 2187. I'm getting negative 80.96 approximately. Negative 80.96 if you round to 2 decimal places there. Okay. Now, does that answer make sense? Before we move on, does the answer make sense? This would give us, right here, negative 72, negative 78, negative 80, and then 2/3, so negative 80 and 2/3, and then it kind of shrinks more and more. I guess maybe it never reaches 81, and I'm kind of accepting of that notion there, that it never reaches 81. It's taking 1/3 of something over and over. So yeah, I'm feeling that one out. Negative 80.96 makes sense as an answer. Now, what is an exact fraction? Let's see if the calculator does convert that. I have a convert to fraction on calculator. Sometimes it doesn't want to help you. It's a little too large. It does. It does in this case. This one, negative 81 over 2187 apparently reduces well enough. I guess you can divide it by 81. 2187 divided by 81 is 27. So this turns into negative 2186 over 27. And you can't reduce that farther unless you go to your, unless you go to the mixed number, which I assume, 26 over 27, looks like it's probably also exactly negative 80 and 26/27. I'm never really asking for the the mixed number version, but that would be kind of what's leading you up to there. And yeah, there's that answer there. That wasn't unheard of, that you can check and see how we can reduce fractions there. Always try and live with that the way you can. Because look, clearly this part, it's not going to reduce with this part here. So I'm not going to try and multiply 81 with this first, the same way I didn't multiply 54 with the 2 first. I divided by the 3 first because I could. From there, or excuse me, I divided by 2 first. I divided by 2 first because I could. So right here I tried to say, how can we reduce this fraction? And the answer, apparently, they both divide by 81. There are only so many numbers that divide by 81 that you are very aware of. And, 9, 27, 3, and 81. Okay, number 5. Same-ish, we have 8 terms here. What we need this time, we do have the value of the first term. It's spelled out right in front of you here. That is 4. This time you are going to need the common ratio. This is times 2. 8 divided by 4, 16 divided by 8, 32 divided by 16 is 2. So establish what your common ratio is so you can work this thing out as well, and they give you the number of terms, which is 8. So we're going to use the same formula here. The value, the series for 8 terms is a sub 1 times 1 minus 2 to the 8th power divided by 1 minus 2. All right, let's see how many parts I can do without the calculator here. 4 times 1 minus 2 to the 8th, I think, is 256 over negative 1. So check that out. 4 times negative 255 over negative 1. So negative times negative is a positive. That divided by 1 does nothing. You're essentially just doing 4 times 255. 4 times 250 is 1,000. 4 times 5 is 20. So I think this should be 1,020. There we go. Yeah, just keep doubling 4 more times to get all 8 terms if you did it practically. All right, last one for finite geometric series here, where everything's negative. Again, we still have to find that common ratio. Now, do the instructions state these are all? I know, okay, it says evaluate each geometric series described. So for better or worse, y'all, when a common ratio is, now I'm not saying this one's hard to find. I think we can clearly find out what it is. But what I was going to say is you don't have to figure out that this is a geometric sequence, which means you don't have to check each time that it's multiplying by the same thing. You're just going to have to trust that it is. Because if it isn't, then that means the problem makers, like me, the problem makers screwed up. Because if they call it a geometric sequence, that means there's a common ratio. So find the only 2 terms that you'd like to find to determine what is the common ratio. What are you multiplying from negative 1 to get to negative 2/3? Well, because the signs are the same, that means you're multiplying by a positive, and 1 times what gives you 2/3? That answer is 2/3. So that's really the only thing that you need to find out there, that the common ratio, by the way, the first term is negative 1. Your common ratio is 2/3 there. You could double check it and just, you can try with other numbers. 2/3 times what is 4/9? Well, 2 times 2 is 4, and 3 times 3 is 9, and that continues there with your 2/3 talk. Now, if it's not so obvious, because it's very possible we're going to run into one. If it's not so obvious, let's say these were your 2 best numbers to work with, and you didn't know how to multiply those things out. I'm not saying what I'm going to tell you is going to be a lot easier, but we're going to run into some that are kind of hard to do. So what do you do if they're hard to do? You always have to do 1 divided by the other. What is negative 8 over 27 divided by negative 4/9? And that is negative 8 over 27 times negative 9/4. And then you reduce this fraction beforehand if you can help it. Negative over negative is a positive. 8 over 4 is 2 over 1. And 9 over 27 is 1/3. And you can see 2 times 1 is 2. 1 times 3 is 3. 2/3. So you get a common ratio of 2/3 regardless how we work it out. Okay, let's go ahead and move forward with this. We have this information. Let's spell this thing out. And we get, give me a second. How many terms? 9? All right. S sub 9 equals A sub 1 times 1 minus r to the 9th power over 1 minus r. All right, a couple things I can clean up before I really go to work here. 1 minus 2/3 is 1/3. Dividing by 1/3 is the same as multiplying by 3. If I multiply negative 1 by 3, I get negative 3. So that works in my favor there. Without, again, you can go straight to calculator, but you'll be approximating a decimal. I'm going to first go with the exact one before I do anything else. Negative 3 times. Now, 1 minus 2/3 to the 9th power. 2 to the 9th, was 5/12. So 1 minus 5/12 over, and then 3 to the 9th, 3 to the 9th. All right, we're getting 19683. Now, I want to give you a heads up. This can't reduce. If 2/3 couldn't reduce, then multiplying by 2 over and over on top and 3 over and over on bottom shouldn't be able to reduce either. Now, what is 1 minus that? Well, what is 19683 minus 512? That's going to be 19171. So again, I'm going for exact answer for you guys. I'll give you the approximate after. You could have typed that in the calculator at any point in time. 3 should be able to reduce with 19683 because 19683 was 3 to a power, right? It was actually 3 to the 9th power. So 3 over this should actually give you a denominator that's 3 to the 8th power. 19683 divided by 3 is 6561. So this will give you negative 19171 over 6561. And again, unless I'm mistaking myself, there is no reason to believe that that should be able to reduce any further. Maybe I'm making a mistake in my thought on that, but I believe I'm going to kind of try that, and I'll give you the decimal approximation as well. And then we'll see if the answer kind of makes a little bit of sense. Yeah, I don't see it. So I think that's the exact way to go there answer-wise. The approximation to 2 decimal places is negative 2.92. Negative 2.92. All right, does the answer make sense here? Negative, well, this is going to be harder to see, but negative 1 minus 2/3 minus 4/9. One thing we know for sure is it is, let's see, what I'm trying to say. It is less than negative 1. It's going to a larger negative because we just only subtract. And we're not subtracting much more. Negative 1 minus 2/3 is negative 1 2/3. Minus 4/9. Okay, that already got into negative 2 territory. And, you know, it's shrinking, but you have 9 terms to go. And I guess it makes sense that it's getting close to, I guess, that negative 3 row. Okay, so those are the answers for the front side on finite geometric series. Let's move on to the back. Determine if each infinite geometric series converges or diverges. Okay, let's start talking about what an infinite geometric series is. An infinite geometric series, of course, is a series that runs infinitely. Same thing's true for an arithmetic infinite series. The difference is in an arithmetic infinite series, if I did like 2 plus 5 plus 8 plus 11 plus 14, etc., my common difference being 3 means I'm just going to keep adding 3 each time. And if I add to my positive numbers, it's just going to get larger positive numbers. Larger to the extent that it keeps going on forever toward infinity, even larger forevermore. And a geometric series can do that as well. If I multiplied by 3, like this, I mean, what's the difference here? It looks like the same thing's happening, only in a larger extent. This would also go toward positive infinity, and of course there are ways you can go toward negative infinity. Now, when you see an instance like this is what is known as divergence, which an arithmetic series always does. Divergence is where you do not approach a finite value that approaches positive or negative infinity or doesn't approach any particular number at all. And when I say approach, I'm thinking asymptotically. I'm thinking that it might not ever exactly reach that number unless we just assume that infinity happens here and through infinity that we converge on a number. How can we converge on a number in a geometric series infinitely and not in an arithmetic series? If the geometric series is shrinking. And I don't mean negatives. I mean if your common ratio is less than 1, like a half, or a third, or 2/3, or 2/9, or 7/8, or whatever. It'll converge if your number's less than that because we see that shrinkage. You saw that. You saw that over here when I was bringing it up with some of these numbers here. I said taking a third over and over. No, which one? It was the first one here. I said, I know that this 1/2 plus 1/4 plus 1/8, etc. If I kept adding over and over, this sum will approach 1. It'll never pass 1, but it will approach 1. That's why I said I knew that it couldn't surpass whatever, 85 something, 86. So the same thing goes here. So our basic rule for this, for convergence versus divergence, and then we'll have to state more on it later, but in an infinite series, if your common ratio's absolute value is less than 1, we have convergence of an infinite geometric series. If the absolute value of r is greater than or equal to 1, you have divergence. Now, I don't like to think of a geometric series having a common ratio of 1 or negative 1. I suppose it's possible to mention it in that way, but then you can give other mentions to it if it was just a positive 1 or so. But all I know is in that case it would also diverge as well because it doesn't approach a single value. So I'll include the equal to. But for the most part, we consider r to be either. Now, when I say absolute value of, I mean even in a negative form. If I do 4 minus 2 plus 1 minus 1/2 plus 1/4, common ratio like that, if I alternate signs over and over, that's not going to change the fact that it will still converge. It'll go up, down, but it'll shrink toward a certain value, which we were kind of looking at before. So there's convergence if the common ratio is less than 1, between negative 1 and positive 1. And divergence if it's outside of that negative 1 or positive 1 thing over here. Okay, so all we have to do really is in each problem just look at what your common ratio is. Common ratio here is 4. Who cares what the value of the first term is, assuming it's not 0. As long as it's not 0, then your common ratio being 4 means that this thing will diverge. This series, infinite. If we went infinitely, 1 plus 4 plus 16 plus 64 plus 256, that would diverge. This one here looks crazy, but it shows that it's an infinite geometric series. Goes from 1 to infinity, plugging in values for m. Looks crazy for a first term, I'd agree there, but there's nothing you have to calculate. Negative 2/5 is your common ratio. Your r is negative 2/5, and it can be negative as long as it's between negative 1 and positive 1, a fraction less than 1. it'll converge. So because of this, it converges. And that's the only proof that I need for that. Whatever the common ratio is gives me proof as far as whether it converges or diverges. This sequence here appears to be geometric. It seems to be dividing by 3 each time, but that's not the ratio. You're multiplying by 1/3. That's what you need to state. The common ratio being 1/3 means it is between -1 and +1. This is also convergence of this geometric sequence, infinite geometric sequence. And lastly, this one here, -1 -2 -4 -8, it's going further negative. And whenever I said as long as the numbers go smaller, I didn't mean smaller like negatives smaller. This is going toward negative infinity. It's getting larger as negatives go. Your common ratio is 2. That is more than 1. This is a divergence. This series diverges. Diverges. All right. So those are the 4 right there, just stating whether they converge or diverge. Now, divergence means that it approaches positive or negative infinity, which means we don't need to evaluate those geometric sequences should they occur. If we're trying to find a sum, we can just state diverges. There is no sum. Because it's infinite, it goes on forever. Positive, negative infinity, sure. But it's got more to it than that. All right, determine the common ratio of the infinite geometric series here. So the S is also S sub infinity. It states that there's an infinite number of terms there. So it says when you start with a first term of -3.5, there's some common ratio that if I multiply this by my next number and add over and over, it should converge at this number, and we want to know what it is. In order to do this, we have to know what the infinite geometric series formula is, and it's this. To find the infinite geometric series sum, it's going to be a sub 1 over 1 minus r. Now, this is taking this formula here, and it is applying the notion that we are only using this formula if there's convergence. And if there's convergence, that means that there's an r value that is less than 1. And this is important because what happens when you substitute infinity in for n with a common ratio raised to the infinity power? If this common ratio is more than 1, if it's more than 1, it's being raised to the infinite power, infinity, right? Going on forever. But if it's less than 1, a fraction less than 1, it's going to shrink towards 0. This thing will dissipate. You'll have a sub 1 times 1, which is a sub 1, and you'll have 1 minus r, which is that. So this stems off of this formula right here, right? We're using this one, and we only use it in the sense of convergence. A simplified form of this, as n approaches infinity, is going to be this when r is less than 1. So again, we're only using this given that the absolute value of r is less than 1. Okay. Now, the common ratio things we solve clearly will have to be that for this thing to work. I mean, that's just how the answer is going to work. So imagine or assume you're going to get an answer that's like that. Now, we might get some decimals because this one's presented as a decimal. I'm fine with that. This one's not, so we'll kind of see how we work it out. So S is S sub infinity. That is -35. Let's plug it in and solve for r. -35 equals a sub 1 is -3.5, and this is over 1 minus r. So we solve for r. This is an algebraic thing, and if you know anything through algebra stuff, whether this was 1 minus r, whether this was x, what have you, if you multiply both sides by the denominator and divide both sides by this thing right here, these effectively switch places. I'm not going to get deep into this right here. This is you can use algebra how you do. Multiply both sides by 1 minus r, divide both sides by -35. You're going to get 1 minus r equals -3.5 over -35. Now, I'm still good on this part right here. This is exactly 10 times larger than this is, and a negative over negative is a positive. So I also know that this is 1/10. Oh, what did I say? Decimal. This is exactly 0.1. You can play with it how you'd like to, but that's what I know. Subtract 1 from both sides, and that's going to be -0.9. Therefore, r equals 0.9, positive. So apparently 0.9 is the common ratio that I multiply this by 0.9, and I get another number. And I do this infinitely. And these numbers add toward and converge toward -35 overall there. That with that common ratio, your infinite geometric series will add to that. And that's what that means. Okay, number 12. -32 is the first term, and S is this. Same thing, we're going to substitute -64 over 3 equals -32 over 1 minus r. I kind of like this one even more because instead of trying to think too much on that algebra front from what I did for switching places, we could consider the cross multiplication version. I know some people don't like to use that term, but I'm okay with the idea as long as you know how to use it. So cross multiplication here gives you -64 times 1 minus r equal to negative 32 times 3, that's negative 96. You could distribute or divide. I'm going to go and distribute to kind of save fraction face for now. We'll get a fraction as an answer later, and we'll deal with it when we get there. So negative 64 times 1, negative 64 times negative r. I add 64. Oh, where's my r? I add 64 to both sides, this 64 here, and I get 64 equals negative 32. Oh, where's my r? What am I doing? And I divide both sides by 64, and I get r equals negative 32 over 64, which is negative 1/2. Exactly negative 1/2. Apparently, you take half of negative 32, negative half of negative 32. You divide it by negative 2, and you add and stuff over and over, you get negative 64 thirds. Negative 64 thirds, guys, is negative 21 and a third. So it's getting a little closer to 0, but not quite fully. Obviously never becomes positive. There's no reason it should. But that is your r value, your common ratio. Okay, so now you have some instances of how you can solve for r there. I probably should have had this one last in my set, but this was just using the formula in a nutshell here. Now we're going to use it the other way. Find the sum of your infinite geometric series given the same formula. So now you're given right here, straight up, value the first term in common ratio. So on this first problem, let's find the infinite geometric series sum. It's a sub 1 over 1 minus r. That's it. 2.4 over 0.5. Dividing by 0.5 is dividing by 1/2. That's multiplying by 2. You get 4.8 exactly. And again, this is what it's converging toward. This is what that answer is. Take half of that over and over. And it looks like it becomes double what it was. Ain't that something? Will that happen again? This time we're taking 1/2 of something again as it appears. And this is you recognizing what's happening here with this sum and series. This is the value of the first term. This is your a sub 1. This is your common ratio. And those are the 2 bits of information that we need. In a geometric sequence, that's the explicit formula. So s sub infinity equals negative 8. I'm betting it's going to be negative 16 over 1 minus 1/2, which is negative 8 over 1/2. Just negative 8 times 2, which is negative 16. So twice over. If you take half of something over and over, it's going to approach double what it was before, which is actually true. Number 15, 2 plus 4 plus 8, etc. Well, your first term is 2, and your common ratio is also 2. Now, do I plug it into my formula? Do I say s sub infinity equals 2 over 1 minus 2? Well, let's see what happens. We get 2 over negative 1, which is negative 2. Is that the answer? 2 plus 4 plus 8 plus 16, etc. converges toward negative 2? Not really, right? Something doesn't seem right with that. I think we assumed something wrong, and we did. This formula only applies, where is it? If the absolute value of r is less than 1, right? Otherwise, it diverges. We shouldn't be doing all of this right here. This is not how we approach it. This common ratio being more than 1, meaning it means the sequence diverges, there is no sum. It approaches positive infinity, but it diverges. There is no sum. We do not evaluate it. You don't use that formula in that case there. All right, number 16, negative 2.7 minus 1.89 minus we have to figure out what we are multiplying by over and over here. So negative 2.7 times r is that, and times r. We have to figure this out. I'll be honest, I don't know it off the top of my head for sure. So what we do is we do a division. Now, if you're unclear on that division thing that I state, when I state you take one number and divide by the one before it, like this, that to get r, this is what we're going to do, which is what we're going to do. Set it up as an algebra equation. Instead, if you're confused on that notion, and if I ask you negative 2.7 times what gives you negative 1.89, set it up algebraically. Negative 2.7 times r is negative 1.89. How do you solve for this? You divide both sides by negative 2.7. How is this any different from what we're going to do up here? It's not. So if you're uncertain, use the algebra that you should know how to do in this kind of scenario to get that one. So negative 1.89 divided by negative 2.7 is exactly 0.7. This is the common ratio we're going to use here. We have a value of the first term of negative 2.7. So let's go ahead and find out our infinite sum here by doing negative 2.7 over 1 minus 0.7. This is going to be negative 2.7 divided by 0.3. I don't want to be wrong, but I think that's a -9. I think it's -9. Let's -2.7. I don't want to be wrong. I script some of my decimal things if I'm trying to overthink it. -9. S sub infinity equals -9. So this is what it converges toward. As 0.7 was less than 1, we can use it. It converges there. And as I look at the numbers, I think I agree with that result. It's going to make sense. All right, so that ought to do it for this one, guys. And yeah, infinite geometric series for people is arguably easier than the one before because all the math you have to do, the extra information you need. But that ought to do it for that one. And you have now learned all of them outside of contextual word problems, outside of... There are some other kinds of questions I could have asked, but now you see the bases of them. You see all the formulas that will be applied. Your next videos that you see will be some review things, just a potpourri of them. So kind of really trick questions, so to speak, but you know, they'll ask you to perhaps explore it a little bit more, a little more varied. And I'm just going to go through them like I assume that you've seen all this stuff before. A little less teaching, a little more doing. I can kind of maybe provide the formulas as we go. But that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. Take care. I will see you in the next one.